Okay, so I'll breeze through these first ones fairly quickly. One of the things that will come up at the end here is to recognize that this angle theta and this angle is 90 minus theta. We're going to have some identities that are based on sine and cosines equivalences with 90 minus theta, either today or Friday. And so always think of that as just being the opposite angle to that to the angle that we're normally talking about. Okay, so define sine, cosine, and tangent as the opposite over hypotenuse and adjacent over hypotenuse. Keep that straight. These formulas here are very practical things to be able to do some quick calculations if you need to in the real physical world. And then, of course, you use the Pythagorean theorem to find the side that you don't know in a right triangle. And when you have ratios, integer ratios, you can always lay out what's called a reference triangle like this, because all similar triangles have the same characteristics of the angle. So, you know, this 5, 3, and then this turns out to be 4 is just as easily spoken about as if I would have written this as a 1, 3/5, and then calculate 4/5. So that's the equivalence between a squared plus b squared equals c squared. That's the same thing as saying sine squared plus cosine squared of theta equals 1. Okay, so I had you try a couple of these. And now let's talk about angles that are greater than 90 degrees. And all the functions, the 6 trigonometric functions that we're going to be dealing with, are all defined for angles that are larger than 90 degrees. And so one of the things that we're going to do, here let me kind of start this one over just to build it. One of the things that we're going to do is we're going to use reference triangles or reference angles in the unit circle. Let's say if we have, you know, on the unit circle this coordinate pair x and y, I can define this other theta sub r as the reference angle. And so by using the reference angle, I can calculate all my values of sine, cosine, tangent, by using these dimensions in here, and that will give us the values of sine, cosine, tangent for the actual angle. Now the thing that we have to modify on getting these things is that the reference triangle and the reference angle are always positive. And so if you remember the way we look at quadrants, we have in different quadrants we have different signs, like above the x-axis y is always positive, below it's always negative. So we're going to make some modifications, and let's say I have this point here as minus 3/5 x and y is 4/5. That would be a point on the circle, and so we can prove it to ourselves that this is indeed a right triangle just by taking these things squared. And we look at the reference angle as having the cosine of the reference triangle where everything's positive, and then we look at the values to see what is positive, what's negative. And in this case, remember the value on the x-axis corresponds to the cosine when the radius is 1. Okay, right? Because the x divided by the radius, 1, will give us just the cosine equals x. Okay, so we're going to look at this thing, this unit circle. And when I'm talking about the unit circle, what this means is that the radius of this thing is 1. All right? And this simplifies all of our calculations, like I said. When you take the cosine, which is the adjacent over the hypotenuse will always be 1, and so we can get values directly out of them. And so these things then just become, directly reading out what these values are. Now, of course, everything is on the circle, and the unit circle has a radius of 1. That means that sine and cosine are always between 0 and 1. It can never be larger than 1. It's, of course, can be less than 0. It can be -1, but strictly speaking, it's always between -1 and 1. The tangent is different, though. You can have ratios, so the tangent can get really as large as, it can go all the way to infinity. So let's look at the quadrants now. We number these in the order that the angle increases. So where x and y are positive is quadrant 1, and then it goes quadrant 2, 3, and 4, counterclockwise around the unit circle. So if we look at the angles, in quadrant 1 it's between 0 and 90. In quadrant 2 it's between 90 and 180. In quadrant 3 it's between 180 and 270. And in quadrant 4 it's between 270 and 360. And this is going to, unless we're dealing with examples of measurement, word problems essentially, I'm going to stop talking about angles as being degrees, and I really want you to start thinking about angles as radians. And so the equivalent radians are between 0 and pi over 2 to pi, pi to 3 pi over 2, and then 3 pi over 2 to 2 pi. And it takes a little while to get used to that, thinking of exactly how much is 5/4 pi radians. I mean, where does that lie as an angle? It takes a while to get the notion down that, well, that's a little bit greater than 1, and it's greater than pi, a little bit less than 3/2 pi, so 5/4 pi is in quadrant 3. But it's something that the more you use radians, the more you'll get accustomed to it, and the more it'll help you. Okay, so let's look at the signs. Sine is SIGN of the trigonometric functions. And so in quadrant 1, since x and y are all positive, all the values of sine, cosine, and tangent are positive. Now in quadrant 2, y is positive but x is negative. So since the sine only involves y, it stays positive, and the cosine and tangent, since they deal with x, are negative. In the third quadrant, both x and y are negative, and so the sine and cosine are negative, but if you take the ratio of sine and cosine to get tangent, both of those cancel out, or both of those negative signs cancel out, and you get positive. And then quadrant 4, x is positive, but y is negative. And so your sine is negative, cosine's positive, and the tangent is negative. Okay? And it takes a little thinking to make sure this is solid. And there's some acronyms on how people memorize this kind of stuff. And I have a hard time even remembering what the acronym is, much less what the acronym stands for. So, just think in terms of your normal XY graph as being the two axes here, and then remember when y is positive and when y is negative, when x is positive and when x is negative, what does that necessarily make the sine, cosine, and tangent for you then? Okay, so here's a couple examples. Let's say we have an angle that is between pi and 3 pi over 2. What quadrant is that? Third quadrant. Okay, so the cosine is going to be -5/13. So what would the sine be? This is a lot like your homework, only now we're in different quadrants. So what's the sine of of the angle when the cosine is negative 5/13. Well, I'll have a few of these for you to try, but since you've started thinking about it, this is the way I recommend you think about it. Okay, so we have our reference triangle. The cosine is a nice ratio, 5 and 13, so I can put 13 as my hypotenuse and 5 as my adjacent. So you start to recognize that this is a 5, 12, 13 right triangle, or if you want to compute it, 13 squared minus 5 squared. The square root of 144 is 12. So this is the reference triangle, and so you know then that the y value is going to be 12 or negative 12. And so we're going to have these ratios, but it's not going to be 12 over 13 and 12 over 5 necessarily. We're going to look at where that is in the third quadrant. You see, and so this is somewhere down here in the third quadrant. And so both x and y are negative. Your radius is always positive. And so the sine then has to be negative. And the tangent, since it's the ratio of the sine and the cosine, both of them are negative. That makes the tangent positive. So you calculate the angles just the way you did in that homework set last night. You calculate the angles, and then you figure out what quadrant are you talking about, and what are the signs that are associated with that. Got it? Yes?
How exactly were you able to determine it on the chart, or on the graph?
On the graph? Like this one here?
Yeah, how did you, yeah.
Okay, all the way around the circle is pi over 2, or is 2 pi. Halfway around the circle is pi, and then halfway between pi and 2 pi is 3 pi over 2. So that's what puts it in the third quadrant for me. Always think in terms of halfway around the circle is pi. Okay, so if you're going to be a little bit over pi, and this one has a range that pi is here, and then if you're only adding a half a pi, that's 1/4. That's 1/4 of a way around the circle. So if this starts at the division between the second and third quadrants, this one starts at the division between the third and fourth quadrants. Yeah.
Could you maybe put the triangle in the circle for us?
Yeah.
Yeah.
Okay, so what we're really talking about, so in the unit circle now, okay, this thing has a radius of 1. And so the cosine is going to be the x value, right? And so the x value is 5/13, which is a little bit under half. So it's going to be here. And so this is the triangle we're talking about. So this is 5/12, and this is 1. Okay, so then this side becomes 5/13, sorry. And this becomes 12/13. Now, this is negative, and this is negative as well then.
And just to make sure I understand, the angle is from the origin?
This is the angle here. So I'm not telling you what that angle is yet. We haven't really gotten to the point of that. Sine, cosine, tangent are transcendentals, so there's no quick formula. I mean, I can plug it into my calculator and figure it out, but Michelle.
If you were given instead of a cosine equals negative 5/13, what if it was the tangent was negative? Would that change?
Well, the tangent in this quadrant is never positive. So there's no solution to, if my angle is between pi and 3 pi over 2 and the tangent is something positive, there's nothing there. Okay, there's no...
But isn't the tangent positive 12/5?
Oh, yeah, excuse me. What am I thinking? Of course, it's the ratio of the sine and the cosine. So if you were given the tangent
Negative.
is if it's, you couldn't be given a negative tangent here.
Oh, okay. I think I
If you were given a positive tangent, then you know that both x and y have to be negative. So the way you would normally calculate it here, you'd actually do it down here.
It'd be like a different quadrant if it was tangent was negative.
Yes, yes. Negative tangent is always in the second and fourth quadrant. I don't know if I misstated what I said when I initially started answering your questions, but
So, like, I understand we're gonna slap even more than 360 degrees in it, but I guess, like, how do I put this? And this, like, this came up last night, but like, the relevant angle is within a single quadrant, right? Like, how do
what you're talking about is the reference angle. Okay, so when we're dealing with the reference angle, that's going to be measured from the x-axis, and so this is our reference angle. So when I drew my little triangle with the 12, 13, and 5, this is my reference angle. And so this angle is going to be something that exceeds pi. Okay, so then my reference angle, whoops, not Q, is going to be 1/8, shame on me, pi, or our angle minus pi. Okay. All right, so here's a bunch of them for you to try. I want you to fill in this table. And I'm giving you several values. And I'm going to tell you what quadrants they are. But I want you to go through and fill out the rest of these. And this might be a better exercise after we do the unit circle, complete the unit circle, but you certainly have enough information to do this now. All right, so it's just a little bit of Pythagorean theorem here, and yeah, in answer to your question about rationalization, -2 over radical 5, in my book is just fine, but other teachers may feel differently. If you're working a calculator, -2 over the square root of 5 is faster to input than -2 square root of 5 over 5. So, and your calculator's accuracy shouldn't be affected by that. Okay, so let's have some key angles here. And so I'm going to start talking about some of these angles that are going to appear on the unit circle. But there's a few that you should remember. Now, the actual axes are not in a quadrant per se. They're in the boundaries between the quadrants, and we call those quadrantal angles, which is not an important term for you to know. If you know, I mean, you can kind of surmise what it's suggesting. But when the angle is just 0, the sine is 0, right? Envision that, where you have no angle. The sine corresponds to the y-axis on the unit circle, so that's 0. Cosine corresponds to the x-axis, which is 1. Tangent is 0 over 1, which is a perfectly good 0. Okay, so then the next one is sine of 90 degrees is the same as sine of pi over 2. And that is the other way around. So the sine is 1, cosine is 0. The tangent, though, now is going to be 1 divided by 0, which is undefined. And so don't ever put undefined or infinity or anything like that. It is just simply undefined. We're going to get to graphing these functions. And, of course, when you have an undefined value in your function, you get asymptotes. And so the graph of a tangent has asymptotes. Okay, so I guess the other thing is pi over 2. Just always think of that as 90 degrees. That's your right angle, is pi over 2. All right, more key angles. Now, let's say I have a 45-degree angle or a pi over 4 angle on this triangle. So that opposite angle is also going to be pi over 4, right? Because you add up to get, add up all the angles, you should get pi, and so we already have pi over 4 plus pi over 2 makes 3/4 pi, so you're ending up with 1/4 pi as that as well. So that says that this is a symmetric or an isosceles triangle. And so when you do, well, you can lay this out as having, 1 as the as each of the bases, and so your hypotenuse becomes square root of 2, and so the sine of pi over 4 is going to be square root of 2 over 2, and the cosine is going to be exactly the same thing, square root of 2 over 2, cosine of pi over 4. And the tangent, since the sine and cosine are equal, the tangent of pi over 4 is 1. So the pi over 2 over the square root of 2 over 2 always appears in pairs, right? Because that just makes that 45-degree or isosceles right triangle work. Okay, so let's go to another triangle that we know about, and that would be an equilateral triangle. And so an equilateral triangle, of course, has all the angles equal, so if the sum is pi, then the any given angle is pi over 3. And let's cut this in half now. So we have this triangle that you would call a 30, 60, 90 triangle, where this is going to be 60 degrees, this is 30 degrees, and this is 90 degrees. Or better, pi over 3, pi over 6, and of course pi over 2. And so if we do the math around here, notice that with an equilateral triangle all the sides are the same, and so here we have C equals 1, B, since we've cut this thing in half, B is going to be 1/2, and then we can figure out what A is by using our Pythagorean formula, and we get square root of 3 over 2. All right, so I remember square root of 3 over 2 because that one has a 3 in it, and a 30, 60 degree triangle has a 3 in it, right? The 45s, those are equal, so those are square root of 2 over 2. The 30, 60, 90 triangles have square root of 3 over 2 in it. Now it's just a question of remembering which of the sine or cosine is square root of 3 over 2. So let's look at the sine of pi over 3. So that's the larger one, where this is the larger angle, and so the larger angle is going to have the larger size, which is square root of 3 over 2. Square root of 3 over 2 is about 0.7, right? It's 0.7071, I think, something like that. And, of course, this bottom leg is going to be 1/2, so we're going to get the cosine of pi over 3 is going to be 1/2. So 1/2 and the square root of 3 over 2 always appear together. They're a paired. And then when we take the ratio, of course, we're going to get square root of 3 over 2 divided by 1 over 2, which will just give you the square root of 3. Now, if we flip the thing around and we're looking at our primary angle as being this one up here, as being pi over 6, then we can swap A and B as the adjacent and opposite, and we get the other angles. So the sine of 30 degrees, or the sine of pi over 6 is 1/2. Cosine of pi over 6 is square root of 3 over 2. And the tangent then is going to be 1 over square root of 3, which is just the square root of 3 over 3. So this is the tricky one because you got a denominator of 3. All right, so we have 6 angles here. No, we have 6 values for the sine, cosine, and tangent of 2 angles. And then we have 2 values for the sine and cosine of pi over 4. And then the initial set of values of 0 and pi over 2, we have 6 values there. So we're starting to build up quite a library of angles and sines. So let's look at the first quadrant of what's going to be this unit circle. Now, remember the radius is 1, and so since the x and y values correspond to the sine and cosine, we can write, or it's actually the other way around, the cosine and sine, we can write the coordinates of these points right along the circle here. And then of my quadrantal angles of 0 and pi over 2, and then look and see where the sine of theta is and where the cosine of theta is. And this should be the thing that burn in your brain. This becomes second nature this semester, where if I'm looking at the cosine as being this x dimension here, then that means that for this first angle, and I didn't write in the angles yet, I think I do have them. Yeah, here they are. So if I look at the 3 angles that I have, so for pi over 6, the cosine is square root of 3 over 2. The cosine of pi over 4 is going to be the square root of 2 over 2. The cosine of pi over 3 is going to be 1/2. So we read that first coordinate as the cosine. The second value in the coordinate pair is going to be the sine, because that's the height of it. That's the y value. Now, if you remember this, and if you remember this business about the reference angles and things, just by knowing this one quadrant and then knowing what happens to the sine, whether it becomes positive or negative and all that kind of stuff, you have, let's see, you have 1, 2, 3, 4 times 4, you'll have 16 different angles that you'll know the sine, cosine, and tangent for. And then, of course, in a few minutes, the secant, cosecant, and cotangent.
Wait, so I'm still very confused. So would it be in quadrants 2 and 4, x is related to the cosine, but in quadrants 1 and 3, the cosine is related to y?
Cosine is always related to x.
That totally
Okay?
confuses me.
So when we have this angle here, unit circle, this is the cosine. When we have this angle, this is the x value, that's the cosine, because the angle is defined as the adjacent over the hypotenuse. And so the adjacent angle is always the x-axis, because that's where we're starting from.
Well, what if can you show me that, for instance, in quadrant 2?
Sure. So if we have unit circle, quadrant 2, and let's say this is going to be or 2 pi over 3. Okay? So then my reference angle is going to be what?
Oh, my reference angle comes from the bottom? It doesn't just...
Always comes from the x-axis. So it becomes 1/3 pi, right? Because 2/3 pi and 1/3 pi equals pi. And so then this here, which is now going to be negative 1/2, is the cosine of theta. So the cosine of 2 pi over 3 is negative 1/2. Okay, everybody following? Okay, and of course the quadrantal angle, theta is pi over 2. And you can see here we have the values of the cosine of 0 is 1, the sine of 0 is 0, the cosine of pi over 2 is 0, sine of pi over 2 is 1. Okay, so now you have this worksheet, and you get to fill in the rest. And actually there's two parts. I have the triangles up on top, and you might want to just start out by labeling those, just with the relevant sides. Remember how I developed that you have the hypotenuse of the 45-degree triangle is pi over 2 and all that kind of stuff. So you could start with those, kind of recreating those from the lecture earlier, and then fill out the coordinates of each of those points along the circle, and start with the unit circle the way it is right now. Then on the table, what I want you to do on the bottom is just label all your angles as you're progressing around and determine the values of sine, cosine, tangent. Don't worry about cosecant, secant, and cotangent yet. Okay, so other functions. You've heard me say this, and you're probably aware that these exist. The cosecant, the secant, and the cotangent are defined as the reciprocals of the sine, cosine, and tangent. Now, I don't know. My brain says that the secant should be the reciprocal of the sine, and the cosecant should be the reciprocal of the cosecant, but that's not the way it is. The cosecant's reciprocal is the sine. Reciprocal of secant is cosine. Now, these are functions that are less used now. They become relevant when you're dealing with some of the identities, and probably in most applications you won't be using them except to perhaps simplify some expressions. Now, a long time ago, when people used to do celestial navigation with sextants and follow the stars and things like that, the secant was a very, very important function. In fact, it was more important than the sine. And there was something called the Haver sign, which is related to the sine, which is a function that is archaic now. Probably people who studied trigonometry way before I did know what it is very easily, but we just don't ever use it anymore. Those were used in celestial navigation, and we simply don't use those. We use sine and cosine and tangent mostly. These are secondary. You should be able to make substitutions back and forth by just looking at the reciprocals. So if we were to formally define these, this would be the hypotenuse over the opposite side, or in the unit circle would be 1 over y. The hypotenuse over the adjacent side, 1 over x in the unit circle. And then the tangent is the adjacent. Oh, did I mess that up? That's not adjacent over hypotenuse. Oops. This is the adjacent over the opposite. X over y. And maybe I correct that, I don't know. Oops, that was too fast, I know. Okay, so be familiar with the definitions. We're going to be handling these functions in some of our computations, but they're less important. Okay, so let's look back at identities again. Now there's a whole lot of trig identities, and a lot of them come from just this particular one. You should just know this one like you know the Pythagorean theorem. Sine squared of theta plus cosine squared of theta is 1. Now, if I were to divide through by cosine, straight through, okay, all I've done is I've taken everything divided by cosine squared and then did my substitution. The sine squared of theta over cosine squared of theta is what?
Tangent squared.
Tangent squared. Okay, so if I'm going to make some substitutions here, I'm going to get the tangent squared of theta plus 1 equals the secant squared of theta. So here you can think of secant and tangent as being paired up, just like sine and cosine are paired up for one of the identities. And then if I did exactly the same thing, only dividing through by sine, and made my substitutions, what I get is 1 plus the cotangent squared of theta equals the cosecant squared. Now the world is restored to order because all the cos are in one equation and all the non-cos are in the other one. So, I guess you can't have it all make sense all at once. Okay, so those three identities are identities you should know. Now, I don't ever remember the second and the third one. I always remember this, and I divide by either sine squared or cosine squared, and I know my definitions to get to the other ones. This one will be fairly important in calculus when we're doing integrations and things of that sort of transcendental functions. This one's going to come up a bit. Not quite so much this one, but certainly this tangent squared theta plus 1 is going to be an important identity. Okay, so we have 1 minute, and I'm going to just show this out. These are the things that you have to know. The definitions of the 6 functions, the 3 main identities, the ones I just showed you, and then the values of the 6 trig functions for all those angles. Now the way to do this is to remember how to get to, how to get to the other ones using those values and reference triangles. Okay, so if you remember those first 5 values and then apply your positives and negatives by quadrant, you'll know the rest of these. Now, I'm not going to be like old Ben Kingsley, my algebra teacher in high school, who would give us a sheet of these things, of random, what's the tangent of 7 pi over 6, and he'd give us 100 of those and ask us to do that in 4 minutes. So I'm not going to do that. There's no reason to be that fast at it. He thought there was. But anyway, you should be able to, with some thought, arrive at these without reaching for your calculator. Certainly not reaching for your calculator.
Wait.
Yes?
So the ones that are circled in red for the values of 6 trig functions,
Yeah.
so those are the main ones, but what about the pi and pi over
All these other ones happen because they are in the second, third, and fourth quadrant of the unit circle. So if you remember the first quadrant, you can construct the second, third, and fourth.